Welcome to the afternoon no, it's not the afternoon session, right? Welcome to the last session in the morning, and it's also the last session today, I guess, because after lunch we'll have the excursion. So the first speaker is Serge Gaspers, and he's talking about parameterizing by the number of numbers. Okay.
Going to work with Mike and Fran, and thank you. Yes, I'm going to talk about non-graph problems. Okay, let's get started. So parameterized complexity is all about asking when does your problem become tractable. So for example, okay, your problem might be NP-hard, but what happens if the max degree is bounded, or what happens if the tree width is bounded, or some other structural parameter? So for what parameters does the problem become tractable? And so in the field of parameterized complexity, all positive results can be related to this picture. So FPT algorithms are just algorithms where you confine the combinatorial explosion and you want it to be small in K. K is the parameter. Kernels just want to restrict the whole size of this picture. And so we have to define this K, so we want to find relevant parameterizations. So for many interesting problem instances, this parameter is small, and we can exploit it and get efficient algorithms. So there are many parameters around, so I list some of them, but the list is much bigger. So there are many graph parameters, like all of these. Solution size is a widely used parameter. But what about numerical problems? So there's not so much work going on in this direction. And let's look at one numerical problem, subset sum. So the input is a multi-set of integers and one special integer s. And you ask if you can select some integers from this multiset such that they sum to s. So parameterized by solution size, this problem has been shown to be W1 hard by Fallows and Koblitz. So now we could just give up and say, okay, parameterized complexity doesn't work for this problem, and we just give up. But you could also think, well, there are instances when I can efficiently solve this problem, so when is it exactly that I can solve this problem? Or identify some good situations when the problem becomes tractable. So we want to think now about some structural parameters here for these numerical problems. And the one we propose is this one, the variety of the multiset in the input. And so given the multiset, its cardinality is, of course, the number of elements, including repeated memberships. And the variety is the number of distinct elements in the multiset. So if the multiset is a multiset of integers, we talk about the number of numbers. So our subset sum problem, we parameterize now by the variety or the number of numbers in the set A. So now I want to know, is this FPT or W1 hard? And it might take some time, but when I tell you that you use integer linear programming, you can quickly see that this problem becomes fixed parameter tractable. So integer linear programming is just the input is an integer program. All variables must be integers. And the parameter is the number of variables. And this problem has been shown to be FPT by Lenstra in '86. So let's say that in our input for subset sum, the number AI occurs mi times in this set, in this multiset. And so then you can just write a straightforward, simple IPL program for this. So xi is the number of times AI will occur in the solution set. Of course, it must be a non-negative integer. Every element can occur at most mi times because there are mi of them. And so the sum of all elements must be equal to our required integer. So, and then the number of variables here is bounded by the number of numbers, and so this problem becomes FPT. And similarly, we can easily show that the number of other numerical or classic numerical problems become FPT, like partition or three-dimensional matching or three-partition. So they are all straightforwardly translated into IPL, integer linear programming, and so ILP, yeah. And so they are fixed parameter tractable. Okay, now we want to get somehow deeper involved into this parameterization, and so we thought about some more meta problems that capture a lot of numerical problems. So I introduced mealy machines, and then we'll see some problems about mealy machines that are, we think, widely applicable to numerical problems. So this is a mealy machine, so it's just a finite state automaton. But on each transition, there's a letter that is read on the input tape, but we also output a letter. So the input is a word, and then you start in some starting state, and then on reading a letter, you go into a next state, and you output letter. This is a deterministic mealy machine, but in general, I will be talking about non-deterministic ones. So for a state and a given input letter, we might be able to go to different states, so a set of states instead of just one state. Okay, so formally, a non-deterministic mealy machine is this 5-tuple, where we have a finite set of states, a starting state, an input alphabet, an output alphabet, and a transition function mapping a state and an input letter to a set of corresponding couples of states and output letters. Okay, now where the number of numbers comes into play is this one. So we want that, okay, we feed our mealy machine a word, or we want it to decide if there exists a word, such that the output of the mealy machine satisfies certain properties about number of numbers. So we want that the output word, so we want to constrain the number of times each output letter is written on the output tape. So for each letter of the output alphabet, so this is the output alphabet, we give it a number, so the number of times it should be written. And then we first ask the following. So given a mealy machine and an input word, x, and a census requirement, so the number of times each output letter should be written. Parameter is the size of the description of the machine. And the question is whether there exists a computation of this machine on the given input word, generating an output word that meets the census requirement. So we're given mealy machine, an input word, and we ask, can you make it run in such a manner that the output word writes A this number of times, B this number of times, etc. So, and then by reduction from multicolor clique, we showed that unfortunately this problem is W1 hard. And but we also give a simple dynamic programming algorithm showing that it is in XP. So notice that what is unbounded in the input here is the size of X of the input word. So we have to somehow describe the graph, which is an instance to multicolor clique. So we have to describe it in X. So, and then build a machine that does all this stuff. Okay, now I give you less information. I don't give you the word X in the input, so you have to guess this word. So I give you only the mealy machine and a census requirement. And the question becomes, does there exist an input word for which a computation of the mealy machine on this input generates an output meeting the census requirement? So, of course, this problem seems harder because you also have to guess the input word. But in fact, the problem becomes now fixed parameter tractable. So in comparison to the other mealy machine problem, in this problem, you were driven by input word. So you had to make certain choices. But now, as you can make certain choices, the problem becomes easier. So I want to give you a flavor of the proof of this FPT result. So first, we look at digraphs. Because our path through the machine, it can be modeled by a digraph, so a path in a digraph. And we say that given a digraph, two paths are arc equivalent if they pass through if for each arc, they pass through it the same number of times. So this means for us that a given letter is written the same number of times. And then there's a result that so any directed path can be replaced by another directed path, which is arc equivalent to the first one, such that the length is at most n squared, where n is the number of vertices, and which has some short loops, where each of these loops begins and ends at the same vertex of this underlying path of length at most n squared. And each of these short loops has length at most n. So we'll get a path and in the graph. And so on this path, we have some short loops where these loops can be executed arbitrarily many times, but you always come back to the vertex you started from. Okay, so for our mealy machine problem, we first make it a digraph. We make the machine a digraph by adding dummy states to make the digraph a simple digraph. Yes, because our mealy machine might have had multiple transitions between two states, so we just add some dummy states. And then we go over all transitions paths in the machine of length at most size of s squared. So s was the states of the machine that start from the starting state. Okay, so we look at such a path, and then we go over all loops, over all short loops that occur on this path. And then we again check by integer linear programming if there exists a set of integers x, where each of these xi's tells us how many times each of these loops is executed. And yes, so the variables of our integer linear program are these xi's, and they tell us, well, the constraints are a word output by a computation of this machine, moving from the starting state to the last state on the path, executing xi times each short loop, meets the census requirement. So this gives you a flavor of how we do this. And I give you some applications of these mealy machine problems. So the first one is heat-sensitive scheduling. So the input are unit job lengths, unit length jobs, sorry, each having a numerical heat level hi. And we want to execute these jobs on a processor, and we don't want the temperature of the processor to go beyond a certain threshold Tmax, and we want to meet a deadline D. So the processor cools in a linear fashion. So the processor temperature is given at some certain time t plus 1 is given by the temperature at the previous time step plus the temperature of the job that is scheduled divided by 2. So we have linear cooling of the processor, of the heat of the processor. It might be that no job is scheduled. And so we want to meet this deadline without exceeding this temperature threshold. Yes, so, but we relax this problem to be able to attack it. Yes, by the way, the NP completeness proof of this problem uses arbitrarily many heat levels asymptotically close to 2. So all these HI, so that there were many of them which were all different, but all very close to 2. And we thought maybe this is not very, this doesn't occur very, very often in practice, that they all have almost the same heat level, but they slightly differ. So we want to do some discretization of the heat levels. So we say that there are only 2 K equally spaced heat levels. So they cannot be arbitrarily close to each other, but distinct. And so with this representation, it's also, yeah, it's not so bad to look at this relaxation, where the heat level at each time is an integer. So because, well, in practice, when you look at the heat level, you don't look at the 7th decimal after the comma to determine do I schedule another job or not. So there's some approximation in the modeling here of this problem. So by a simple formulation of this problem into our exists word mealy machine problem, which was FPT, so we can show that so parameterized by K, this problem is also FPT. The other problem I'll talk about is splits reconstruction for paths, where, well, a split is the following. A split of a path is the following. So you have a path V1 to VP, and the weights are W1 to WP. And the split of the edge between vertex I and I plus 1 is the following thing. So if you remove an edge, the path falls into 2 subpaths, and the total weight is on each of these subpaths is just the sum of the vertex weights, and the minimum sum of the vertex weights on the left of this edge, and the vertex weight and the total vertex weights on the right of this edge is called the split of this edge. This problem, yes, the problem is given a multi-set of vertex weights and a multi-set of edge weights, is there a weighted path where the vertex weights are assigned to the vertices of the path and the edge weights are assigned to the edges of the path, such that each edge weight is the split at this edge. So this problem comes from computational chemistry, more precisely from drug design. And here we look at the parameter number of vertex weights, because, well, I don't know, in drug design you might only have a certain number of molecules that you want to assemble in order to obtain this path here. Okay, and so this problem easily reduces to a special case of the other Mealy machine problem, namely a given word Mealy machine problem. And I think it's a really interesting open question whether this special case is also W1 hard. We think so, but we have not been able to prove it. Okay, so I can conclude my talk. In practice, many problems come in a weighted fashion. And so we think that parameterizing by the number of numbers is a really interesting way of exploiting the numerical structure inside these problems. Our first application shows that, okay, we can move the approximation issues, like discretizing the heat levels, to the modeling instead of to the algorithmic algorithm. I give you two problems where I want to know whether they are FPT or W1 hard, so two concrete problems. One is the splits reconstruction for paths, and the other one is a subset product, parameterized by the number of numbers. Okay, thank you.
Thank you very much for the interesting talk. So questions?
I was a bit puzzled actually by your comment on this heating schedule problem. So the product construction would lead to instances where, well, you have nothing like evenly spaced intervals or heating levels. But now with the FPT result, you assume this, right?
Yes, yes.
So is this NP complete?
So the question is whether our relaxation is indeed NP complete, and yes, well, if you don't bound K, you can do still this construction of arbitrarily many heat levels that are close to each other. Yes.
Okay, by sort of
if you let K be very, very large, yes.
Okay.
But it might be interesting for bounded K, if you for K equals 5, if it's NP complete or not. Oh, yeah. Sorry. Yes, sir.
You asked at the second slide whether there were other parameters that you might look at. I wondered if we know anything about subset sum. If you parameterize on the number of distinct prime factors of the numbers involved, like if they're all multiple, some power 2 and 3 or 5, 3, 5.
Mm-hmm.
Do we know anything about that?
No, I don't, but might be very interesting to look at it, yes. And yeah, just one remark. I've seen another parameterization of subset sum, which involved the size of the description of the integers. And the result was that it's FPT parameterized by this plus the size of the solution.
Let's thank the speaker again.
Okay, so hope everybody is still sort of alive. So it's just the last talk before lunch, so then you can revive again and enjoy the afternoon, especially with a nice excursion. So actually this talk I think should have been given by my former PhD student Daniel, who has moved away from academia at this moment. So therefore I'm presenting this because the very question which is underlying this talk is how and under which circumstances is it possible to translate this idea of measure and conquer, which is so successful, was so successful for analyzing search tree algorithms in the exact case, into the parameterized framework with the classical parameterizations. So that was the basic gist of the whole thesis of Daniel, and so this is one of the core parts, I would say. And so that's just an overview of my talk. So I will first get a little bit into this question, what's measure and conquer and what's the problems with applying this to or within the parameterized framework. Then I will list 3 problems which I would like to talk about a little bit, make you familiar with those, and finally concentrate on one of those, namely connected vertex cover. And then I will conclude somehow, hopefully, in the end. So, as I already mentioned, measure and conquer is quite popular in the area of exact algorithms, and it gives you some kind of technique to get an amortized analysis of search tree algorithms. The intuition is quite simple. You have to somehow balance better and worse situations, and this means, for example, that you just know that if you have, for graph problems, say, the situation that small degree graphs are nice for you, but also if you find very large degrees, it's fine for you, so then you somehow may be able to balance out these things, but because by branching you somehow work towards smaller graphs, and somehow this should pay off for you. But then most often it is the case in this exact analysis that you can actually point your fingers to the place in the graph where you can actually kind of do something about the budget. So you may, because you are creating better situations, you may already get something from that future branch. That's the basic idea behind in many cases. And this is exactly the point where things tend to be non-trivial in the parameterized setting. So, because these local arguments somehow slip away. If we try to use this idea within the parameterized setting, then sometimes it's also possible to actually localize what's going on. So our very first attempt to use some kind of genuine measure and conquer analysis for a parameterized branching algorithm was on maximum acyclic set of on cubic graphs. And there, if you think for it for some seconds, it's actually the case that you can really see that actually the parameter is not very small, to be honest. So therefore you can somehow localize where you can move on your budget in order to get it done in the classical, I would say, classical fashion of measure and conquer. But in general, this is not so clear, and it wasn't clear to us since sort of the very end of the thesis, where we finally got examples how you can actually have something like a global budget management in terms of the parameter, having some sort of parameterized measure, and this is one of the things I would like to show you in the following. But there are more subtle issues around if you try to talk about measure and conquer in connection with parameterized algorithms. For example, you have to make sure that you know a point-time answer once your measure drops below 0. So the measure is somehow describing the complexity of your graph, and suddenly it drops below 0, and then you must say immediately yes or no. And if you are not sure that the traditional budget, K, has dropped to 0 at that time, then what can you do? You have to argue about it. That's part of mathematics which slips in, which doesn't occur if you argue with a parameter n, say, so in the exact case. And finally, you must also ensure that the reduction rules you use never increase the measure, which could happen if you are not careful about this. There are some kind of easy ways to get a measure and conquer analysis into the parameterized realm of problems. For example, if you have some kind of linear size kernels, then you might first kernelize and then apply the sort of standard techniques nowadays for the exact measure and conquer algorithms, measure and conquer analyzed algorithms, and then you have something like parameterized measure and conquer. But it's a little bit of cheating, right? So therefore, actually, finally, Zesh, well, you know him, just the previous talk, he asked in a parameterized newsletter the question whether it's at all sort of possible to do some kind of parameterized measure and conquer when you don't have linear size kernels. And the example I gave before with this maximum acyclic subgraph thing, that has a linear kernel, for example, although we do some kind of parameterized analysis on it, or did it. So what I will try to describe are actually three kind of related problems where we could do some kind of measure and conquer analysis and which don't have small size kernels unless something happens. And this something will be more specific for the examples. So in order to illustrate what I'm doing, I will use some kind of graph example. And since we are drawing close to Christmas, I thought somehow of this kind of German children's nursery rhyme, which is basically a kind of funny drawing problem. You will know if you're German, you might know if you're non-German. I don't know whether it's sort of international. So the task is, this is a kind of, this is the house of Nikolaus, which means for each syllable you draw one line, and you should draw this little picture without having to jump. So it's just one draw, so it's a kind of little riddle even to do with this. So in case you are getting bored with my talk, just try to do this on a piece of paper. I gave some hints actually with these arrows. And it's also kind of nice graph theory because, of course, if you think about degrees of this graph, blah, blah, blah. Anyways, so I'm taking this as a starting point to get a graph out of it. And I did it a little bit more complicated to make it more interesting. So this will be my sort of standard graph example. And so now I'm in the position to present you the problems I will talk about. Connected vertex cover, what is it? So we are looking for a vertex cover of size at most k, such that the graph induced by the vertices in the cover is connected, as the name kind of indicates. For instance, these blue guys form a connected vertex cover, as you might verify. Question is, of course, is this a minimal solution or not? Well, we come to that point later. What's known and new about this problem? So actually, it has quite some history in terms of FPT algorithms, where the parameter is here, and it will be in general with my talk, an upper bound on the size of the solution we are looking for. So Gu, Niedermeyer, Wernicke gave a 6 to the k algorithm, which is actually 4 to the k, just if you plug in some another Steiner tree algorithm. And so we improved it a little bit to 2.9, and actually Möller, Richter, Rosmanit had at the same time basically a paper something like 2 to the 7, something to the k, and we will get down in this talk to 2.4882 to the k. So this will be the result which I will try to at least outline a little bit during the talk. And this actually implies a 1.86 something to the n exact algorithm, which is also kind of new because I don't know any exact algorithm for that problem. Maybe you guys know. I mean, better than the 2 to the n. That always works, of course. According to kernel sizes, Dom, Lokstanov, and Saurab had an ICAL paper last year where they showed that, amongst other problems, also CVC doesn't admit a pole-sized kernel unless something bad happens. So, in a sense, this is therefore since we apply actually measure and conquer techniques here, kind of one of the answers to Serge's problem, and similar things with the next problem. Edge dominating set. So actually this has kind of IPAC history I will show later, so therefore it's quite fitting to present it here. So we are now asking for a set of edges that dominates all others and is of course bounded by K. So you can also think of it as a classical domination problem in the line graph. So in our example, so these blue lines indicate an edge dominating set for this graph. And you can easily verify in this case that's the minimum one, right? So one doesn't do it. As simple as that. Okay, so what's known about this? Well, the IPAC history sort of started in 06, where I had a 2.6 something to the K algorithm using polynomial space. Then basically Baudelaire and Van Roy had a technical report where they used basically a result of Fomin, Gaspar, Saurabh, and Stepanov, which finally ends up to something like 2.4 something to the K, using actually exponential space. And what we'll do in this paper is using again polynomial space, you get something like 2.38 something to the K. So the numbers are now not so sort of impressive, but the differences in the usage of exponential versus polynomial space. And actually, yesterday on the bus, Johan told me that in his thesis he improved this figure to 2.4006 to the K, right? But nonetheless using exponential space. And actually we can also use exponential space and we would get up something like 2.373 to the K. So still a little bit better, but obviously there seems to be some boundary kind of. Anyways, what about kernels? In this case, we actually know a quadratic vertex kernel. And the question is, can it be better? And in this case, we don't have something like ETH in the background, but $100 from Daniel. So it's at least something if you can show anything on that kind of direction. So that is also good, and a kind of solution to Gaspar's problem. And the third problem, which is actually not in the proceedings, but I just wanted to mention it, is total vertex cover. So what's that? So we again look for a vertex cover of size at most k such that, and now the condition is that no, this is not true. So that in this graph, yeah, this is true. Yeah, that this has a minimum degree at least one. At least one. Yeah, that's true. So there are no isolates in the induced graph by C. So that's this is kind of a natural. Well, you might know total dominating set. So this is kind of similar to that. And in our case, this gives you a TVC if you just take the endpoints of the EDS, which we found before. Okay, so what's known and what's new? Actually, nothing is new here. So we had a 2.3 something to the K algorithm, and the point is, unfortunately, if you and using pulse space, and if you look into that paper a little bit more detailed, you can say that this is also a kind of measure and conquer analysis. I wasn't aware of that so much. When we wrote that, that was way before sort of we thought about measure and conquer in parameterized algorithm, but in a sense it is. So therefore it fits here, and actually we tried to beat ourselves here with a sort of real measure and conquer analysis, which we now know, and we got really the same figures, so it's obviously some kind of boundary hit there already. Anyways, that paper is also kind of awkward to me, but I should at least tell you the truth. So we also claimed a quadratic size vertex kernel there. And, well, 3 years later, or now this year, we had a paper where we showed that unless ETH fails, there is no pole-size kernel. So the problem is that this argument is simply wrong, but it's kind of instructive to really find the error. So we didn't find it, so we wrote it down and we were happy with it. And also the referees were happy. And so actually, well, this paper actually is in the last 2 years among the 20 most downloaded papers from that journal. So many people looked at it and nobody wrote me that something was wrong with that. So anyway, so it's kind of instructive to look at it, but I shouldn't advertise errors too much, I think. So anyways, so this is a third kind of answer to Gaspers's question, this time the other way around, because there was this kind of measure and conquer analysis before, and later we proved this non-existence of a small kernel. So again, another solution here. So what do all these algorithms have in common? Well, they first enumerate minimal vertex covers up to a certain size, k or 2k, depending on the problem. And then they do something with these obtained solutions as a kind of guideline. For example, in case of CVC, they use some Steiner tree phase. In case of edge-estimating set, you can apply some maximum matching techniques. And actually, that's Paul time, as you know. And in case of DVC, you have some sort of fitting size set phase afterwards. So this makes all these algorithms look quite alike from above. And the use of measure and conquer is, amongst others, to balance out these phases. And I will focus now on CVC. Oops. Okay. So in order to get something for CVC and also for all the other problems, we need some annotated versions of these to keep track of certain things happening. And in our case, so we will have, in addition, a subset Q of vertices, which we require to be in the final solution. If you think about the branching, what happens? You pick a vertex, either it is in the solution, so you put it into Q, now in our code of formulation, because you won't delete it, you need it for the connectivity requirements, or not. And then you take its neighbors and similar things. Many improvements are based on quite a huge list of reduction rules. And this is interesting in a certain sense because theoretically we know that reduction rules wouldn't lead us to anything in the sense of a kernel size, but they are very helpful in the sense of branching. So therefore I'd like to at least show you some of these. Like we have some small degree rules, degree 0, degree 1, and degree 2 rules, some rules which do something about cut vertices, or also if you have neighboring Q vertices, so vertices where we know they should go into a vertex cover, connected vertex cover, we can merge them. So that's the contract rule. Best explained, I think, by our little example. So we start with this little graph, so forget about the blue at the moment, I should have repeated it. And the first thing, well, it's actually not displayed here, so the first thing would be, I should show this graph again, sorry, I didn't notice. I have the picture, but I didn't put it into the slide. So, so this guy has degree 2, and the rule says then, well, pick not this vertex, but the two neighbors are preferred in a certain sense. So that's the rule. And therefore, we can delete it and mark the neighbors as blue. And similar things happen for this guy here, just degree 2. And we can delete it because the two neighbors are kind of preferred in the solution of CVC we are after. So that's once again this degree 2 rule, which I won't prove, but I just want to make sure that it is applicable. And it is applicable because this graph doesn't contain any isolates, no pendants, no cut vertices, because in this rule list they were listed before, and it's important to test this before. Okay. Yes, I was just confusing these two pictures, so I was too late. So this was the lead rule to that. So then I am here again. So sorry, that was a mistake in the slide. So then I will delete this one and check for the next degree 2 vertex. It's here, so I can apply it again. And now I've already marked 4 vertices being blue, and this guy in the middle now will be marked blue, so it will go into Q as well, because it is now a cut vertex. Now. It hasn't been in the original graph, but it has become a cut vertex, as you can see with the components which this guy is splitting the graph into. So therefore, it must be in the solution as well, because there's no other way to combine, to connect these two components. So, and then we can see that so we have this bluish graph now, and now we can start to apply this contract rule, which says, well, we have two neighboring vertices colored blue. We can kind of connect them, contract them, and so we get here, and after 3 more times we end up with this graph, and actually the degree 2 graph creates the empty graph. What does it mean? Well, it does mean that our reduction rules actually solved the whole instance. So although they were not meant to do this, so they were just meant to help the branching, but by coincidence, this graph's completely resolved, and actually it also proves that this 5-vertex thing is an optimum solution. So we had a different solution on the slides before, but here we see that's optimum. Okay, so again, what's the general agenda? What's the general kind of algorithm we are looking at? First, we probably apply the reduction rules basically in the given order. Secondly, we do some kind of clever branching to get this vertex cover enumeration. And finally, we have this Steiner tree phase, and that can be done by the algorithm of Naylor, for example, ICAP 2009. Yep, any questions? No, okay. So how do we do this branching? Well, quite simple. It's a binary branching, basically. You either put a vertex into Q, so we know that this will be in the vertex cover finally, or its neighbors. That's the classical vertex cover branching. And the thing is that afterwards, usually reduction rules apply. This can be seen especially because of this branching is done in certain stages ordered by heuristic priorities. For example, we say that vertices in these sets take higher priority. I skipped about the definition, but this means vertex V has 1 neighbor in Q and 3 neighbors in not in Q. And this means 2 neighbors in Q and 3 neighbors not in Q. So if I have such a branching, I will branch on it with priority. Why? Because afterwards, because I know there are certain numbers of neighbors already in Q, I will be able to apply the contract rule and things like that. So, okay. So, if I'm talking about measure and conquer, I must sooner or later present the measure. And the measure, in our case, is kind of trivial. And this might still leave some room for improvements, actually. So, this is the whole thing. So it's very simple. If you know other kind of measure and conquer algorithms, this is kind of trivial. So what I'm doing, I'm giving the graph together with this pre-described set of vertices, and I'm just taking the k, which is, and this is a little bit different if you know this classical analysis of FPT algorithms in a search tree case where you always have this initial parameter k, and you consider this as a budget, and it will decrease over time. In this case, no. The k stays fixed. So that's one of the main differences. So, and then we subtract this number of Q vertices which are meant to be in the vertex cover, recall this, weighted by omega. Some omega actually is smaller than 1/2. And we subtract again some C, which measures the number of contract applications and some other rules which I actually didn't tell you much about because this requires some other management of cases which I wouldn't go into. So if you now set up the usual search tree analysis with respect to this measure, you will get branching vectors like these ones. So this is one of the examples. And actually this is this case where you have one neighbor in Q and 3 neighbors not in Q, which is reflected just by this kind of thing. For example, if you take the vertex now in Q, so you put it in the vertex V, then what does it mean? Your measure, you will get gain 1 in this branch. Why? Well, one vertex is moving from Q into C because it will be a contract application, and so this is basically reflected by this kind of thing plus the additional omega which you get. I won't go into details here, but this is just how things are, and then you balance out, find the right omega to do this for you. Okay, so I might at least try to explain a little bit how this measure works with our little example, to make sure that, for example, our measure will never increase our measure. That the reduction rules will never increase our parameter. So this is our parameter. Now what happens if I do the very first step? So I will look at the very beginning, though, so we have no contract applications and things like that. We have no predetermined vertices, and so the measure here will be just the k. If k is 5, it will be just 5, and I will assume omega equals 0.5 in the moment here. And so if I now move these two guys into Q, Q will now be 2, of course, and still none of these applications. But if omega is 0.5, then I will have the measure drop to 4. It will drop. That's good. No increase. I have applied reduction rules. Measure drops. Next thing we did was Q equals 4, so the measure drops again. Fine. Then, then we had this cut vertex rule, and actually this gives you another situation where the measure drops a little bit because Q grows, and now we have the contract rule application, so Q is decreasing, but C is increasing now, so the measure drops again. And finally, we end up with this measure, and we might change this degrees to 0 rule so that finally the measure drops to 0 and the graph is empty. Fine. So, conclusions. I tried to sketch at least how some sort of genuine parameterized measure and conc analysis is possible. And of course, this asks naturally for more questions to apply this technique. And with refined measures, you could also try to improve on our current constant. I think this is in principle possible, but it's just a very kind of nasty task. This exact algorithm I was talking about for connected vertex cover is basically derived by a trick first observed by Raman and Saurabh, just taking the parameterized algorithm and plugging it into a two-way case distinction. Is there something genuine exact algorithm here? I'm not quite sure, actually, because what we finally gain from our parameterized algorithm, and now I have some intuition here, is that you can somehow bound the number of terminal vertices within K, so you can express this. You have no way to do this if you just talk about n. So that might be tricky. And finally, just to mention it, so our EDS algorithm also works in the weighted case. Okay, so it remains, of course, to ask you for questions. But first of all, thanks for your attention. Merry Christmas. Have a nice lunch, nice excursion, and so on.
Thank you. Questions? Okay, no questions. So thank you again. And